Hello again. So in this video, we are going to look at numbers bigger than infinity and different sizes of infinity and how they behave and all these sorts of weird, strange things going on. Now, I'd like to start with a question. Does this sound mystical to you? Numbers beyond infinity, different sizes of infinity, different properties of these weird infinite sets? If it does, let's appreciate the moment of time we're in now. Remember back in the Cartesian time, you had the Cartesians, they believed a scientific explanation was if you can explain a phenomenon just in terms of particles colliding, like they came up with the kinetic theory of heat, that heat is really particles moving around with a lot of kinetic energy to them. And when Newton came around with his theory of universal gravitation, that looked like he was introducing a new occult force into science, and it just seemed mystical to him. Well, we're at another point in history like that too. If this talk of transfinite arithmetic, numbers bigger than infinity and all of that sounds mystical to you, then perhaps we're at just another one of those points. And then it seems like that now it's sort of incumbent on me in this video to make it all sound a little more scientific. Well, we'll see how that goes, huh? All right, so let's see. Transfinite arithmetic was invented by a mathematician named Georg Cantor about 1880s. Cantor was a real analyst, which means he was in the calculus neighborhood of mathematics as opposed to, say, the geometry or the algebra neighborhoods. And he was interested in coming up with a measure of the complexity of a set of points. Now, next I'm gonna just say a few words to few people who know a little more mathematics. If you don't understand what I'm gonna say next, don't worry, it's not necessary that you do, but just stick through it for a second. Cantor was looking to classify when a function had a unique Fourier series representation. And he thought the key was looking at the complexity of the set of discontinuities of that function. And that this measure of complexity of the discontinuities would come up with a characterization of when a function had a unique Fourier series representation. Okay, back to English again. Ready? Good. As you may have heard some of those words I said, he was interested in coming up with a measure of complexity on sets. And what happened was this. He came up with a measure of complexity such that a set could have a complexity 0, 1, 2, 3, and so on. And it so happened that he just ran out of numbers and needed more. So he created more. Let's take a look at the details of this measure of complexity. What was it that he was doing? All right, so let's say a single point in isolation, no other points around it, we're going to say has Cantor-Bendixson rank. That's the measure of complexity 0. Okay. Now, if a point is a limit of a bunch of Cantor-Bendixson rank 0 points, like all of these points are sort of hovering by themselves, so they each have Cantor-Bendixson rank 0. But this point right here is a limit of those. We say that point has Cantor-Bendixson rank 1. And we say the whole set, the complexity of the set is the complexity of the most complex point in it. So this set we'll say has Cantor-Bendixson rank 1. All right. Now let's take the same picture. Actually, you know what? I'm going to make these points vertical slashes. It's going to make it a little easier to mentally parse what's coming up next. All right, so we have a picture here which is supposed to be just like the upper one, except now we have slashes. And what if we create a bunch of points limiting to each vertical slash, so that this point right here, instead of Cantor-Bendixson rank 0, has itself Cantor-Bendixson rank 1. And we'll come up with a sequence of points limiting to here. So again, this point here also has Cantor-Bendixson rank 1. And we do that again and again, so that each of these points has Cantor-Bendixson rank 1. Well, then the point here, which is the limit of those points itself, we say has Cantor-Bendixson rank 2. So you have Cantor-Bendixson rank 2 if you're the limit of Cantor-Bendixson rank 1 points. And let's repeat that picture again one more time just so we see what's going on here. If we take this whole sequence here, this Cantor-Bendixson rank 2 sequence, and we insert it here and here and here and here to make all of these points here Cantor-Bendixson rank 2 points, then this very last one, the one they limit to, has Cantor-Bendixson rank 3. And again, from what we said before, this set right here has, the whole set we say has Cantor-Bendixson rank 2 because the most complex point in it has Cantor-Bendixson rank 2. And this set here we say has Cantor-Bendixson rank 3 for the same property and all that. Okay, now what Cantor wanted to show was that nice things happen, again, to the mathematicians, if the set of discontinuities was nice enough, had Cantor-Bendixson rank. If nice things happened, or if a set of discontinuities, or if a set of points had Cantor-Bendixson rank, then it was nice. Nice things happened. The function had a unique Fourier series representation. And so we tried to prove it by induction on finite numbers, and you just couldn't prove it and couldn't prove it and couldn't prove it. And sometimes mathematicians, if you can't prove something, you start wondering if it's really true and start looking to see if you can construct a counterexample. Well, let's take a look at this. Let's make a new sequence over here. Boom, 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 boom. And all of these are limiting to here. And now in front of this first slash here, we're going to put this first sequence. So this first slash is going to have Cantor-Bendixson rank 1. And in front of the second slash, we're going to put the second sequence in here. So the second point now has Cantor-Bendixson rank 2. And in front of the third slash, we're going to put this next sequence. We're going to stick that in there. So this point has Cantor-Bendixson rank 3. And similarly, we repeat the process. We have Cantor-Bendixson rank 4, 5, 6, and so on. So here's a question. What's the Cantor-Bendixson rank now of that last point? What it has to be bigger than 1, 2, 3, 4, 5, 6, so on in every finite number. We run out of numbers. So what Cantor did, he just created a new one. He said, well, let's call that number omega. That's the last letter in the Greek alphabet. So now we have this set has Cantor-Bendixson rank, and in fact, this set has Cantor-Bendixson rank omega. But it doesn't stop there. Let's take our sequence again here, and let's create a bunch of slashes limiting up to here. And let's take our omega sequence here and stick it in every gap there. So each of, and this one here, so each of these points has Cantor-Bendixson rank omega. What's the Cantor-Bendixson rank of this last point here? Well, I guess that's going to be the next number. We might as well call that omega plus 1. So similar, so we have 1, 2, 3, on and on and on. Then we run out of numbers. We need a new one. Well, we'll call that omega. And then we have omega plus 1, omega plus 2, and on and on and on. And eventually, we get omega plus omega, which we can write as 2 omega. And as you can imagine, we can have a 3 omega, 4 omega, on and on to like an omega omega or omega squared. I'm running out of whiteboard, much less running out of sanity. We can have omega squared, omega cubed, on and on up to omega to the omega, and it just keeps going. Now, hold on a second. Cantor was able to show that if a set had Cantor-Bendixson rank, either finite or infinite, it was nice. Discontinuities, unique Fourier transform representation, so forth. But he knew that the sticking point in his proof would be selling other mathematicians on all of these transfinite numbers. So what's a guy to do? So he has to come down and sit down and come up with a whole theory of these transfinite numbers so that mathematicians would buy him for his proof. Now, in all honesty, eventually he really fell in love with these things and they became the object of his attentions for their own sake. But necessity is the mother of invention, and this is where his interests in all of this stuff came in. This is where it came up from. So what kinds of stuff do we stick numbers on? We 1, 2, 3, 4, and 5. We put these numbers on like collections of things, sets of things. And so he saw the way of developing this new theory of transfinite numbers is to look at sets and set theory. So set theory became his approach that he developed in order to develop this new theory of infinite numbers. All right, so now when you start developing the set theory of infinite sets, some weird things happen. You know, this might work against my efforts to try to convince you this is all very scientific, but some weird things happen. First of all, there's two ways you can use numbers. There's an ordinal number and a cardinal number. Ordinal numbers are an ordering, a placement. Like if you have a horse race, horses can come in first, second, third, fourth, fifth, sixth, seventh place. Cardinal numbers are just how many in a pile. You know, if you have a horse race with 7 horses, there are 7 horses in it. So if I say this horse came in 7th place, I'm using the word 7 as an ordinal number. If I say there are 7 horses in the race, I'm using 7 as a cardinal number. And for finite numbers, these two ideas match. This is how we tell the size of sets. When you count something, 1, 2, 3, 4, 5, and then wherever you left off at, the highest, you're putting an order on those objects, and the highest number you end with, the ordinal, is now going to be the size of that set. So the ordinality, the highest ordinality of elements in that set becomes the cardinality of that set. That's what counting is. And that's how we count things. In infinite sets, the notions of ordinality and cardinality diverge. They are not the same thing like they are in finite sets. That is, you cannot tell the size of an infinite set by counting it. I mean, that sounds kind of obvious, but you'll see what I mean in a minute. It gets a little weirder. Now, once we have this distinction, we look at the notion of cardinality. Here's another weird thing that happens in infinite sets. How can we tell? So I just said that we won't be able to count things. We can't correspond ordinality to cardinality. Can we tell if two sets are the same size or if one's bigger than the other without counting them? Well, imagine this. Imagine you're in a classroom and there's a bunch of students in there. And you want to know, are there more students than seats, or are there more seats than students? And you don't want to count them. What can you do? You tell the students to sit down. If all the students are sitting and nobody is sitting on each other's laps and nobody's stretched out over two seats, it's just one student per seat, and everybody's sitting and there's some empty seats, you know there are more chairs than students. If everybody's sitting and all of the seats are filled and there's some standing around the edges, you know there are more students than seats. And if everybody is sitting and there's no seats empty and there's no students standing, you know that there are exactly the same number of students as seats. And you know this without having counted how many students or how many seats there are. So this is a way of figuring out if two sets have the same cardinality without having to count them, without going through the ordinality. Now let me ask you this. Are there more even numbers, or are there more just numbers, like all the numbers? Which of those sets is bigger? You might say there are obviously more numbers than there are even numbers, because the even numbers are a proper part of the set of numbers. And there's numbers that aren't even. But wait, let's take a closer look at this. Let's list the even numbers, 0, 2, 4, 6, 8, and so on. And let's list all of the numbers, 0, 1, 2, 3, 4, and so on. If we think of the top row, the even numbers, as students, and we think of the bottom row, all numbers, as seats, and we tell the students to sit in the seats, every student can sit in a seat. And every seat, if you take a look, this continues on off to the side. Every seat is going to eventually be filled, which means there's no students left over, which means there are the exact same number of students as seats, which means there are just as many even numbers as there are all numbers. So what we have here is that a proper part can have the same cardinality, the same size, the same how many as its whole. Now this is weird, but it's not necessarily a contradiction. Remember, with non-Euclidean geometry, we saw a lot of weird results in there. Sakurai and Lambert thought that the non-Euclidean geometry couldn't possibly be true because of all of the weird results they were getting, like rectangles don't exist or something. But it wasn't actually a contradiction, and eventually people just came to accept this as a different alternate geometry. This is a weird result, but it's not really a contradiction. And so Cantor was now able to develop this theory of transfinite sets, this notion of transfinite size, this notion of ordinality, this notion of cardinality. And although some of the results were weird, they were basically just an exciting new field of mathematics. Since he was doing everything with sets, I'll show you a little notation here. His notation was, let's say X is a set of objects. If we abstract away from all of the properties of the elements of that set and just look at the order they're given to us, we call that X bar, and that's the ordinal number of that set. And if we abstract away from even the order those elements are given to us, and we just look at the cardinality of that set, that's X double bar. And so he started developing this whole set theory and ordinal, cardinal stuff, all that. And this was great. Some mathematicians hated this, and some really fell in love with it, and it became a very polarized issue. Weird, but not inconsistent until it was, because eventually someone found an inconsistency. Not just a weirdness, but a real out and out inconsistency. Okay. It broke people's hearts. Now, what do mathematicians do when they're faced with a crisis? Well, as I've said before, they find religion, by which I mean they go back to that good old Greek riddle. The way to try to save all of this transfinite Cantorian stuff is to look at how did the Greeks do it. They want to start out with a simple set of axioms that are obviously true and reason carefully from those. And hopefully by doing that, instead of using Cantor's naive set theory, they will be able to avoid the problems, avoid the contradictions, and still rescue all of the great stuff in Cantor's theory. Now, ironically, the first person to develop an axiomatic set theory did not do it to rescue Cantor's transfinite arithmetic. A mathematician by the name of Ernst Zermelo proved something. And a lot of mathematicians had a real problem with one of the steps in his proof. He did a move which nowadays we call using the axiom of choice. And they didn't really buy his proof. They didn't think he really proved it. Well, in order to get mathematicians to buy it, he kind of engaged on a two-prong attack. His first prong was to develop an axiomatic theory of set theory in which we lay out the obvious axioms first, and this step, which we call now the axiom of choice, he would stick in there so that you could see along in this whole system, it's very reputable. It'd be reputable by, what was the phrase I had? Respectable by association. You see it in with all of these axioms and you'll say, oh, I guess it is respectable, we'll accept that. His other approach was this. He wrote a lot of mathematicians all over the world and pointed out to them that their greatest results that either made their reputation or were a step in their proof that made their reputation were also equivalent to the axiom of choice. So if they were going to reject his proof as illegitimate, they would all have to forswear their own proofs and give up on the results that made their reputations. Now, I don't know which of these two proofs proved more convincing, but it did so happen that after this program, after this engagement, a lot of really popular, famous mathematicians started accepting the axiom of choice, and they started saying this was okay. And now eventually, another mathematician by the name of Frankel figured out one axiom that should be added on that really was necessary and kind of missing. So we call it Zermelo-Frankel set theory. Despite what I just said, the axiom of choice really wasn't so widely accepted. So it's usually not in Zermelo-Frankel set theory. If we add the axiom of choice in, we now call it ZFC, Zermelo-Frankel with the axiom of choice. But now this axiom set promised to be a rescue of Cantor's set theory and all of the transfinite arithmetic. And the thing is, not only did it do that, but mathematicians soon discovered it could do more. This axiomatic system could be a new foundation for all of mathematics. So just like, remember I said Euclid's Elements wasn't just Euclid's geometry. It started with Euclid's geometry, but it was all of mathematics known at the time. They just thought geometry came first. It had all the arithmetic and number theory in it. And it was just that you had to prove arithmetic and number theory and stuff using geometry because geometry came first. Well, from set theory, we can create arithmetic and we can create geometry and we can create all the other areas of math that have been invented in the time. So this became a new universal system in which mathematics could operate, starting with the axioms of set theory. So this was a new answer to that old question, what's first? Originally, everything was number, then everything was geometry, then everything was the manifold intuition of space and time, and now everything is sets. This is the sort of the new modern system of it. However, there's a problem. Even though we do have this new axiomatic system, how do we know there's not an inconsistency lurking in it? How do we know that it's free from contradiction? How do we know that it won't be the case that it'll break our heart again? Who could save the day? Enter stage left, our old friend, David Hilbert. Is David Hilbert going to do it? Is he going to prove set theory is consistent? Is he going to save the day? Will this story have a happy ending? Of course the story will have a happy ending. Would I be telling the story if it didn't have a happy ending? What do you think this is? Real life? My 18th video is going to be on what we call Hilbert's program, his efforts to prove the consistency of
what now is all of mathematics. Before we do that, you need to understand something called symbolic logic. Symbolic logic is an important part of his program. So for my next lecture, lecture 17, we're going to spend some time to look at the work and life of the inventor of symbolic logic, Hilbert's old sparring partner, Gottlob Frege. So I hope to see you there.